Hello, it's Keith here, and this is lesson 4 of the simple series of my ARM assembly programming tutorials, and we're on the Game Boy Advance and we're only using thumb today. We're going to do an example using thumb mode. Now this is an example from my new book. This is my second book, and this one covers 5 new assembly languages. It covers ARM Thumb, 658.616, 6809, PDP-11 and RISC-V, and it's the same format as the first one, but it doesn't require you to have read the first book. Now we're going to cover 2 of the topics in there: how to draw a bitmap to the screen and how to move it around with the joystick using ARM Thumb on the Game Boy Advance. So let's go over to our code and let's see today's example. Okay, so the example we've got today is this joystick thumb one here. Now what we've got here is a sort of dummy header. This isn't a true Game Boy Advance header, but it is enough for our emulator today, so it will suffice. Now the first thing we're doing at the start of our program is we are actually turning on thumb mode. Now we've got our label here, thumb test, and you can see this assembler directive.thumb here, which tells the assembler to compile thumb code. But what we need to do to turn on thumb mode is we need to do a branch and exchange with bit 0 set to 1 to that address, and so that's what these commands here are doing. These are true ARM commands. It's not possible to start the processor in thumb mode, so we need to switch to thumb mode. That's what that's doing. And then at the start of our program, we're loading a valid stack pointer address here. Now, if you saw the Hello World example I said before, for long immediate values, we can no longer load them in as an immediate. We need to load them at addresses after the line of code for our current line. So we've got various ones here. We've also got our sprite data here, this bitmap. This is our smiley in bitmap data, and you can see the color format here for our smiley. So that's the bitmap we're going to show to the screen. Now the first thing we're doing here is we are setting up the screen. We're basically writing the value 403 to that memory address there. That is the display control that sets the screen up. We're using registers R6 and R7 as our X and Y position here. So we're starting at 10,10 and we're running our show sprite routine. So let's check out that show sprite routine. So this is our bitmap drawing routine here. So basically what we're going to do is we're going to take our X position and multiply it by 16. Why 16? Well, our sprite is 8 by 8 and we're going to move in 8 by 8 blocks, and each pixel uses 2 bytes. So the X position is being multiplied by 16 there, and that's getting our grid position for our X position. Now our Y position, we're basically multiplying our Y position by 240 pixels per line, times 8, that's 8 lines for our sprite, because we're moving in 8 pixel blocks here, and then times 2 because there's 2 pixels per block here. Now we can't load that in immediately, so we've got our line size definition here, and you can see we've defined that here, 240 times 8 times 2. And what we're basically doing is we're multiplying our Y position by that, and that is calculating the offset for the Y position. And we've already added the X position, and then the final thing we're doing is we're adding the screen base. Now the screen base is at that memory address there, and you can see we've got that here as well, another long defined there. So we add all of those together, and that is our VRAM destination. Now our sprite source we load into register 4 here, so that is our bitmap sprite, our smiley. And we are loading into register R8, which we can't move to directly, but we're loading in the amount that we need to add to move down a line. Now basically that is 240 times 2, because that's the width of the screen in bytes, times 2 because 2 bytes per pixel. But we're subtracting 16. The reason for that is we've already drawn the smiley to the screen. The smiley is 8 pixels times 2, so that's 16. So that is the amount we need to add to our current VRAM position to get to the start of the sprite for the next line. Okay, so now all we need to do is move 8 per line. We're using R7 as our X position, and we need to do 8 lines, so we're using R6 as our Y position. And what we're going to do is we're going to XOR, or EOR if you prefer, the VRAM data from the screen. So we're loading in a 32-bit half from our source bitmap in R4. We're loading in the current screen data from R3 into R1, and then we're EORing that, and that's effectively inverting the screen's current data, and we're storing that back to the screen here, the VRAM destination R1. Why are we using EOR? Well, it's simple for simplicity, because this means if we draw the sprite to the same position twice, the second time we'll remove it, and that's an easy way of getting lots of things on the screen but taking them off again as things move around. I would suggest you use EOR if you're just getting started with graphics. It's far easier than redrawing your entire screen using screen buffers, or in other ways redrawing the background data, so that's why we're doing that. Now, after each line, we're increasing our source bitmap destination R4 and our VRAM destination R3 by 2 bytes, 1 pixel effectively, and we're subtracting 1 from our X count. We're repeating for the remainder of the line. Once we've done a line, we're adding R8 to the VRAM destination. Now, R8 is the amount of bytes that we need to skip after each line, and that is moving us into position for the next line. And then we're decreasing R6, our Y count, and we're doing the next line accordingly. Now, once we've finished, we are basically popping all the registers off the stack and the program counter, which effectively returns us. The link register was pushed onto the stack, so that is effectively also a return. So that's our show sprite routine, and that's how we show our sprite, and also how we remove it, because as I say, XOR means that if we show the sprite twice to the same position, we will remove it. Now, when we want to read in our directions, we're using the joystick port, and we just read in from that memory mapped address. Now, the joystick port we've defined all the way down here. It's this memory address here, 4000130. So we just read in from that. And the various bits in that returned value are the various directions and fire buttons and start and selecting things. So we're only interested in up, down, left and right for our purposes today. So what we're basically doing here is masking those bits and waiting for one of them to change. So we're waiting for up, down, left or right to be pressed until it is. We just keep looping here. Once it's pressed though, what we're going to do is we're basically going to remove the sprite from the screen, test the directions, move the sprite, and then show it again. So we need to show the sprite first in the current position, because as I say, that inversion will mean it's removed. Okay, now what we're doing is we're testing each of the bits in order. So here we're testing up, here we're testing down, here we're testing left, and here we're testing right. And in each case, if that bit is not set, we're going to skip the next section. So if that bit is 0, we would jump to joy not up here. But if it isn't 0, if that bit is set, then what we're going to do is we're going to check the current position of the player in that direction. So in this case, we're trying to move up. We check if we're already at position 0, and if we are, we don't want to move anymore because we'd go off the screen. So in that case, we would skip. But if we are not at the top of the screen, we can move up. So we move the Y position up by 1. Here we're testing the maximum bottom position of the screen, which is the screen's 20 tiles tall, so 28 byte pixels that is. And so we're checking value 19 here, 0 to 19. And again, if we're not at the bottom of the screen, we move down. We're doing the same here for left and the same here for right. So we're doing each direction in the exact same way. And then once we've tested each of the directions and moved as required, we're just showing the sprite back to the screen, the new position, assuming the sprite wasn't already at the edge, of course, in which case it'd be the same position, but that would work fine. And then all we've got here is a very crude delay loop, because the arm is very, very fast. So we've got this very crude delay here, just a loop waiting for a while before we repeat again. If we didn't have that, we'd be moving far too fast, and the little demo would be unusable really. We wouldn't see any of the intermediary moves around the screen. So there we go. So that is really all there is to today's example. It's very straightforward really. If you liked what you've seen, please consider buying my book. Obviously, I would certainly appreciate it if you did buy it, but you're welcome to go to the website, just download the source code for today's example for free, because I'm a terrible advertiser. I give all my stuff away for free for some reason, so you can go and do that. You can also see my arm thumb tutorials if you want to see more arm thumb. Anyway, hope you've enjoyed what you've seen today. Thanks for watching, and goodbye.